In the last 2 decades, the contribution of solar energy to the world's total energy supply has grown significantly. This video will show how solar cell or photovoltaic cell produce electricity. Energy from the sun is the most abundant and absolutely freely available energy on planet Earth. In order to utilize this energy, we need help from the second most abundant element on Earth, sand. The sand has to be converted to 99.999% pure silicon crystals to use in solar cells. To achieve this, the sand has to go through a complex purification process as shown. The raw silicon gets converted into a gaseous silicon compound form. This is then mixed with hydrogen to get highly purified polycrystalline silicon. These silicon ingots are reshaped and converted into very thin slices called silicon wafers. The silicon wafer is the heart of a photovoltaic cell. When we analyze the structure of the silicon atoms, you can see they are bonded together. When you are bonded with someone, you lose your freedom. Similarly, the electrons in the silicon structure also have no freedom of movement. To make the study easier, let's consider a 2D structure of the silicon crystals. Assume that phosphorus atoms with 5 valence electrons are injected into it. Here, one electron is free to move. In this structure, when the electrons get sufficient energy, they will move freely. Let's try to make a highly simplified solar cell only using this type of material. When light strikes them, the electrons will gain photon energy and will be free to move. However, this movement of the electrons is random. It does not result in any current through the load. To make the electron flow unidirectional, a driving force is needed. An easy and practical way to produce the driving force is a p-n junction. Let's see how a p-n junction produces the driving force. Similar to n-type doping, if you inject boron with 3 valence electrons into pure silicon, there will be 1 hole for each atom. This is called p-type doping. If these two kinds of doped materials join together, some electrons from the n side will migrate to the p region and fill the holes available there. This way, a depletion region is formed, where there are no free electrons and holes. Due to the electron migration, the n side boundary becomes slightly positively charged, and the p side becomes negatively charged. An electric field will definitely be formed between these charges. This electric field produces the necessary driving force. Let's see it in detail. When the light strikes the p-n junction, something very interesting happens. Light strikes the n region of the PV cell, and it penetrates and reaches up to the depletion region. This photon energy is sufficient to generate electron-hole pairs in the depletion region. The electric field in the depletion region drives the electrons and holes out of the depletion region. Here we observe that the concentration of electrons in the n region and holes in the p region becomes so high that a potential difference will develop between them. As soon as we connect any load between these regions, electrons will start flowing through the load. The electrons will recombine with the holes in the p region after completing their path. In this way, a solar cell continuously gives direct current. In a practical solar cell, you can see that the top n layer is very thin and heavily doped, whereas the p layer is thick and lightly doped. This is to increase the performance of the cell. Just observe the depletion region formation here. You should note that the thickness of the depletion region is much higher here compared to the previous case. This means that, due to the light striking, the electron-hole pairs are generated in a wider area compared to the previous case. This results in more current generation by the PV cell. The other advantage is that due to the thin top layer, more light energy can reach the depletion region. Now, let's analyze the structure of a solar panel. You can see the solar panel has different layers. One of them is a layer of cells. You will be amazed to see how these PV cells are interconnected. After passing through the fingers, the electrons get collected in bus bars. The top negative side of this cell is connected to the back side of the next cell through copper strips. Here, it forms a series connection. When you connect these series-connected cells parallel to another cell series, you get the solar panel. A single PV cell produces only around 0.5 voltage. The combination of series and parallel connection of the cells increases the current and voltage values to a usable range. The layer of EVA sheeting on both sides of the cells is to protect them from shocks, vibrations, humidity, and dirt. Why are there 2 different kinds of appearances for the solar panels? This is because of the difference in the internal crystalline lattice structure. In polycrystalline solar panels, multi-crystals are randomly oriented. If the chemical process of silicon crystals is taken one step further, the polycrystalline cells will become monocrystalline cells. Even though the principles of operation of both are the same, monocrystalline cells offer higher electrical conductivity. However, monocrystalline cells are costlier and thus not widely used.
The journey begins with sand, specifically quartz sand. Most solar panels are made of silicon, which is the main component in natural beach sand. Silicon is abundantly available, making it the second most available element on Earth after oxygen. It's out of the quarry and into the fire. The first stage is to get the silicon out of the rocks, and that's done in this enormous furnace. Temperatures reach over 2,000 degrees Celsius. This is unbelievably hot and also quite dangerous. Silicon is used to make everything from window glass to the processes in your home computer. And without it, a solar panel just wouldn't work. The purified silicon is melted and formed into ingots, which serve as the raw material for solar wafers. These ingots are produced using either the Czochralski process or the float zone method. In the Czochralski process, a seed crystal is dipped into molten silicon and slowly withdrawn to create a cylindrical ingot. This block would be far too big to put on your roof, which is where solar panels usually go. The average roof wouldn't support it, so now it needs to be cut down to size. The silicon ingots are sliced into thin wafers using a wire saw, a process that requires precision to minimize material loss. These wafers, typically less than 200 micrometers thick, undergo surface treatment to remove any remaining impurities and defects. An anti-reflective coating is applied to the front surface of the wafer to enhance light absorption, allowing for greater efficiency in converting sunlight into electricity, and the subsequent drying process ensure optimum surface cleaning. All wafers are then measured by fully automated sensors and cameras, and graded according to their thickness and surface quality. In the next step, each wafer is processed into a solar cell, capable of converting sunlight into electricity. Metal conductors, typically made of silver or aluminum, are screen printed onto the wafer to create a grid-like matrix, ensuring uniform distribution of electrical current. The wafer is then treated in a high-temperature furnace, where phosphorus is diffused into the surface to create a negative electrical charge. This, combined with the boron-doped region, forms the essential PN junction necessary for solar cell operation. Solar panel. After this 6-year class in chemistry and physics, which we did in 3 minutes, we go to the fun part, assemble. The solar cells are interconnected to form a solar panel, with various configurations available depending on the desired output and application. The cells are typically soldered together using conductive adhesives or laser welding, creating a series or parallel connection.
Take me home. I know you wanna. 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 Take me home. Take me home. I know you wanna. I know you wanna. Take me home. I know you wanna. Take me home. I know you wanna. Take me home. I know you
যদি সত্যি বলি বলি তোমাকে তুমি আছো মনের ভেতর আমি হারাই হাতে রাখো হাত কাছে নাও টেনে আমি না বলবো না নেব তোমায় মেনে তুমি ছাড়া অসহায় আছে কি বড় উপায় আমি যে তোমায় স্বপ্নে দেখি নেই আমার অবকাশ কাটে দিন আসে রাত আমি তোমায় স্বপ্নে দেখি স্বপ্নে দেখি না 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 আর নয় লাগে যে ভয় যাচ্ছি ভেসে প্রেমের দেশে যেন লেগে হাতে রাখো হাত কাছে নাও টেনে আমি না বলবো না সাথে যাব চলে তুমি ছাড়া অসহায় আছে কি বড় উপায় আমি যে তো